First of all, you will see what is called buck converter. See, it is also called as the step down converter. Step down converter. See, this is the basic circuit. If I give 12 volts here, at the output of this load, the voltage will be less than 12 volts. These type of converters are called as buck converters. So here we have a switch, a power electronic switch, a diode, inductance as well as capacitor. This switch is controlled by a PWM control technique. See, first of all, what we will see what is called PWM. PWM is nothing but pulse width modulation. Pulse width modulation. A modulation technique is used for turning on and off this power electronic switch. See here, this is the pulse waveform. This is called as T on, and this part is called as T off. Together we will call it as total time. So this on period can be extended as shown here. See here, the conduction period of the switch is decided by this T on time. So there is a parameter called as delta, which is called as the duty ratio. This delta is called as the duty ratio. It lies between 0 to 1. The formula for duty ratio is T on divided by total time T. So if my duty ratio delta is equal to 0.5 means we have 50% T on and 50% T off. This is the meaning. This is the total time T. So with the help of this pulse width modulation control, I can adjust the conduction time of this switch. Now we will see the working of the buck converter. If we give the input voltage as 12 volt here, the output will be less than 12 volt. As we already saw, voltage is reduced because there will be a voltage drop across the inductor. If it is 3 volt, for example, 12 minus 3, the voltage will be here, it will be 9 volts. This is about the buck converter. So here we have two modes of operation, mode 1 and mode 2. Mode 1 is when the switch is turned on, and mode 2 is when the switch is turned off. If we give the input voltage as 12 volt here, the output will be less than 12 volt. As we already saw, voltage is reduced because there will be a voltage drop across the inductor. If it is 3 volt, for example, 12 minus 3, the voltage will be here, it will be 9 volts. This is about the buck converter. So here we have two modes of operation, mode 1 and mode 2. Mode 1 is when the switch is turned on, and mode 2 is when the switch is turned off. When the switch is turned on, the current flows from the source to the inductor. It cannot flow through the diode. Since it is cathode here, it cannot flow through the diode, so it flows through the inductor. Current flows through the inductor, and during that time this inductor will store some energy. There will be some voltage drop depending upon the value of the inductor. Then the current flows through the capacitor. Also it flows through the load RL. So during the switch is turned on, this capacitor will also get charged. So current will flow in this direction as shown in mode 1. Now Now if the switch is turned off, if this inductor, when the switch is turned on, will be this side positive, left hand side positive and right hand side negative. When the switch is turned off, this inductor will reverse the polarity as shown here. This side will become minus and this will become plus. Now this inductor will act as a source and current flows through the load directly. Also, during the on time of the switch, this capacitor is get charged, so this capacitor will also contribute the load current. So there is an increase in the current, there is an increase in the load current, but because of this voltage drop across the inductor, there is a decrease in the load voltage. In buck converter, the output voltage V0 will be less when compared to input voltage, but the current will be high. The load current will be high when compared to the previous case. This is plus, so the current will flow through the load and it will reach here. Now the diode is forward bias and it will be conducting. This will be the current flow direction. Also there will be a circulating current from the capacitor that will also contribute to the current of the load. This is the working of buck converter. This is how voltage is reduced and current in the buck converter is increased. The detailed working explanation is given here. Just you can go through. In this diagram, we can see the when the duration of turning on the switch, the inductor current slightly increases and it cannot instantaneously come down. The inductor current cannot instantaneously come down. Slow. There is a gradual decrease in the instantaneous current. There is a gradual decrease in the inductor current, and the output DC equivalent load current will be the perfect DC voltage. Next we will see about the boost converter. Coming to the boost converter, we have similar to that of buck converter, we have an inductor and the switch is placed in this fashion, that is vertical. We have a diode and a capacitor. Voltage across the capacitor will be the voltage across the load. See, in boost converter, the input voltage will be less than the output voltage. In other words, the output voltage will be high when compared to the input voltage, but the current will be, output voltage current will be less when compared to the input in the boost converter. The same pulse width modulation technique is used to turn on and off the switches. Also we have an inductor here. We have two modes of operation, mode 1 and mode 2. Mode 1 is when the switch is in the on state. Mode 2 is when switch is in the off state. We will see mode 1. If the switch is turned on here, current from the source will travel to the inductor. Here you will be having plus and here you will be having minus. There will be a huge amount of current, large current flowing through the inductor. During this time, this inductor will get charged. The inductor will have the energy in the inductor will increase. So this current will flow through the switch and reach the negative terminal of the battery. So during the switch is turned on, there is a current flow in the inductor, so this inductor will save some energy. This is mode 1. Also, initially if we have any charge in the capacitor will discharge across the load in mode 1. So voltage across the capacitor will be the voltage across the load, V0. Coming to the mode 2, when the thyristor switch or when the switch is turned off, this inductor already stores energy this stored energy will get discharged. When the energy is discharged, it changes the polarity from left hand side positive to negative, and the right hand side negative to positive. You can see here in mode 1 left hand side will be having positive, here in the left hand side we will be having negative. Now these two, if you see here, this voltage source and the inductance are such a way that they are connected in series. As they are connected in series, the stored energy discharges through this diode, through the capacitor, also through the load. So here when the stored energy discharges, this capacitor will be charged. This capacitor charge increases. As we already said, the voltage across the capacitor will be the voltage across the load. Since the supply voltage and the voltage across the inductor are connected in series, the output voltage V0 will increase. That is greater than the input voltage. This is the basic working of a boost converter. It has been explained in detail. Just you can go through the notes. Now we will see the buck boost converter. See, buck boost converter, you can also increase the voltage or you can decrease the voltage at the output, that is across the load RL. So this is mainly done using the duty ratio del. This is also denoted as a D. In some textbook they will be denoting this as D, or it may be delta. This is the duty ratio. Similar to that of buck converter and boost converter, you will be having a switch that is controlled by PWM control technique. We have an inductor, diode and a capacitor. See, initially you must check the polarity. See, the bottom side of the capacitor is positive and the top is negative. So the output voltage would be minus V0. The output voltage is in negative initially. Similarly, we have two modes when the switch is closed and mode 2 when the switch is open. Now we will see what is the operation when the switch is closed. See, when the switch is closed, current from the battery source will flow through the inductor. See, it cannot flow through the diode because it is reverse biased, so this diode will not conduct. So the full current will flow through the inductance and reach here. Also, some amount of the current can also flow through the capacitor, so that this capacitor can get charged. I repeat, when the switch is closed, current from the battery flows through the inductor, so the polarity of the inductor will be plus and minus here. Then it reaches the negative of the source. Also, there is a chance of current flow through the capacitor and it can get charged. It can also get charged when the switch is turned on. Now mode 2, when the switch is turned off, this inductor will change the polarity. Here upper side of the inductor will become negative and lower side will become positive. So there will be a current flow in this direction as indicated here. Current will flow in this direction through the load, and this diode will be conducting and it reaches here. Also current from the capacitor will also flow through the load in this direction. So from the capacitor as well as inductor, current flows. Since the capacitor terminal is reversed, the output voltage will be the voltage across the capacitor, so you will get a negative voltage here, output voltage here. See, if I find the total voltage, by integrating both the modes, for simplicity I am removing the calculation. V0 divided by V in is equal to D divided by 1 minus D, where D is the duty ratio. See, depending upon the value of d or delta, we can decide the output voltage, whether the output voltage can be high or low. See, when the delta is greater than 0.5, when the delta is greater than 0.5, it will act as a boost converter. The output voltage will be more. When the same delta duty ratio is less than 0.5, it will act as the buck converter. Okay, greater than 0.5 boost converter, less than 0.5 will be acting as a buck converter. When it is same, when it is equal to 0.5, your input voltage and the output voltage will be same. So when the duty ratio is exactly 0.5, the input voltage and the output voltage will be equal. So you will be having both buck operation as well as boost operation in the same circuit. So it is called as buck boost converter. Now if you see here, the delta is 0.5. The meaning of 0.5 is 50 from the total time. 50% of the time the switch is turned on, and 50% of the time the switch is turned off. That is the meaning of D is equal to 0.5. You see, this switch is a MOSFET switch or a IGBT switch, which can work at high frequencies. They can work at high frequencies, mostly for domestic applications. The frequency would be 10 kilohertz. The frequency can also get increased. If you know the frequency, you can also calculate the time period. By F is equal to 1 divided by T. So how long this switch is turned on, the time period can also be calculated with this formula. This is about the buck boost converter. Here we have given the detailed explanation about the working. Just you can go through it. Thank you. We will see in the next session. Hello friends, in this session we are going to see about inverters. We have different types of inverters, but in this session we are going to see only about single phase inverters. First of all, we will see what is called inverter. See, inverter is nothing but a circuit which converts DC power into AC power with desired output voltage, depending upon our application, with desired output voltage and frequency. I repeat, a circuit which converts DC power into AC power at desired output voltage and frequency is called as inverters. See, the input to the inverter, as we already know, it is DC. This DC power can be obtained from any existing power supply network, or it may be from a battery or a fuel cell, or even it may be from a photovoltaic array. As we already know, photovoltaic array, the output will be DC. This can also be given as an input to the inverter. See, in this inverter circuit we will be using many power converters such as BJT, MOSFET, IGBT. Also we will be using SCRs, silicon controlled rectifiers. We will be using this SCRs. This SCR is also called as thyristor. Is also called as thyristor. The symbol of the thyristor will be similar to that of the diode, but you will be having additional terminal called as gate terminal. This thyristor can be used as a switch. This thyristor can be used as a switch by controlling the gate input. What is gate? Gate or pulse input, we will say. Gate pulse, we will say. There are different circuits that can generate this gate pulse. For simplicity, I will just draw. See here, this is a waveform where you will be having some voltage above 0. Let it be 5 volt. If this 5 volt appears across this gate, then this switch will be in the on state. If I remove this 5 volt, if it is 0 volt, then again it moves to the off state. So I can control this device, I can control this thyristor with the help of this gate pulse in simple fashion, if you say. Also, turning off this thyristor is not an easy task. If I bring this voltage, this pulse signal to 0, this thyristor will not instantaneously turned off. So you require additional circuitry for turning off this thyristor also. The process of turning off is called as commutation. The process of turning off is called as commutation. So you require different types of commutation circuitry to turn off the thyristor. For simplicity, we are avoiding the pulse generation scheme and also the commutation schemes. The major application of inverter are induction heating. It can be used for a temporary supply in an aircraft power supply, and it is mainly used in home UPS systems. Now we will see the working of off-bridge inverter. When the thyristor T1 is turned on with the help of IG1, when the thyristor T1 is turned on with the help of IG1, current from this Vs by 2 source will flow in this direction and goes through the positive of the load, and it will reach the negative terminal of the battery. So when T1 is conducting, when T1 is on, current flows to the positive of the load. So whatever voltage is applied here, that will be falling across the load as V0. See here in this diagram, whatever voltage is applied, the voltage falls here until T1 is conducting. At this instant, I am turning on T2. At this instant, I am turning on T2. So my thyristor T2 is turned on. Simultaneously, simultaneously the thyristor T1 is turned off in this position. In this time, T1 is turned off. So when T2 is conducting, power will be transferred in this direction. Current flow will be in this direction, that is, current flows from the source and it go through the negative terminal of the load, and T2 conducts and it reaches the negative of the battery. So my voltage will be in the negative direction as shown in the waveform. Again in this direction, that is, current flows from the source and it go through the negative terminal of the load, and T2 conducts and it reaches the negative of the battery. So my voltage will be in the negative direction as shown in the waveform. Again T1 is turned on, so the voltage will shifted to the positive. Then this cycle repeats. This is when the load is not varying, when the load is a restive load, this will happen. This conduction of diode D1 and D2 will happen only when the load changes. If it is, for example, if we are using RLC load, we have two cases. One is over damping. There is a case called as over damped load or under damped load. In these two cases, this diode D1 and D2 will be conducting. When diode D1 and D2 are conducting, current will be flowing from, so I will draw here, current will be flowing from load to the source. Also here, current will be flowing from a load to the, this case called as over damp, or it will happen. This conduction of diode D1 and D2 will happen only when the load changes. If it is, for example, if we are using RLC load, we have two cases. One is over damping. There is a case called as over damped load or under damped load. In these two cases, this diode D1 and D2 will be conducting. When diode D1 and D2 are conducting, current will be flowing from, so I will draw here, current will be flowing from load to the source. Also here, current will be flowing from a load to the source in this direction. So these two diodes are called as the feedback diodes, mainly used for production when we are using different types of loads, heavy loads. This is about the working of off-bridge inverter. Now we will see the working of full bridge inverter. In full bridge inverter, we will be using 4 thyristors and 4 feedback diodes. Thyristor T1 and T2 are triggered here, and thyristor T3 and T4 are triggered here. So when thyristor T1 and T2 are turned on, current from the supply will flow in this direction and it enters the positive of the load. Thyristor T2 will be conducting and it reaches the negative of the load. So whatever voltage is applied here, that will fall across the load. So I am getting the voltage Vs here. At this particular instant, when I turn off T1 and T2, T3 and T4 are turned on. So there is a change in the current direction. So here current flows to T3 and it flows through the negative of the load, and T4 conducts and it reaches the negative of the source. So current flows through the negative of the load when T3 and T4 are conducting. So my voltage will also be negative. Again T1 and T2 are conducting. So as in the case previous case, current flows through the positive and voltage will also be in positive. So this cycle continues. Here we have 4 diodes. Similar way, this operation depends upon the load. Their conduction depends upon the load. Power is transferred from load to the source when they are conducting, when we have different types of RLC loads. This is about the basic working of. Thank you. We will see in the next session. Hello friends, in this session we are going to see about rectifiers. Rectifiers is nothing but an electronic device which converts alternative voltage into unidirectional voltage. As we already know, alternative voltage will be having both positive as well as negative values. This is converted into an unidirectional value that is called as DC. The device which converts is nothing but the rectifier. For converting AC to DC, we require this device requires an unidirectional conduction device, which is most popular called as PN junction diode. See, the symbol of the PN junction diode is this. It consists of two terminals, anode and cathode. This device permits conduction only in one direction. The reverse direction is not possible. So this rectifier uses this unidirectional device, which is PN junction diode. See, depending upon the period of conduction, how long the device conducts, we can classify the rectifier into two major types. One is the half wave rectifier, another one is the full wave rectifier. This full wave rectifier is further divided into two types. One is the full wave rectifier with the center-tapped transformer and the bridge type rectifiers. This is a simple circuit which can convert AC to DC. That is the rectifier circuit. Now we will see the half wave rectifier. See, this is the input of the rectifier and this is be the output. See, this is not a perfect DC, which is also called as the pulsating DC. See, it is in the single direction, only the positive off side. We don't have any negative off cycle here. So this is also considered as DC, but it is not a perfect DC, it is a pulsating DC. This perfect DC can be changed into a perfect DC with the help of a filter. This is called as filter. We have different types of filters called as inductive filter, capacitive filter and many more. With the help of this filter circuit, we can convert this pulsating DC into a perfect DC output. Okay. See, in this circuit, we will be having an AC input. We have a single diode and this is connected to the load. This RL is the load. As we already know, this diode will conduct only in a single direction. The reverse direction is not possible. See, what is the applied voltage? The applied voltage equation is given by, the expression of the applied voltage is given by V in, input voltage is equal to Vm sin omega t. See, this is the mathematical expression for this waveform. If I substitute the value of omega t from 0 to 360 degree, I will get this waveform. So any sinusoidal waveform can be represented mathematically with this formula. Always if you see this Vm, your applied voltage must be greater than the cut-in voltage of the diode. See, cut-in voltage is nothing but the minimum voltage that this diode can conduct. It will be around 0.6 to 0.7 volt. So your applied voltage must be always greater than 0.6 to 0.7 volt. Then only this diode will be conducting. Coming to the working of half wave rectifier, so I will just first draw the circuit here. You will be having a diode here. You will be having a resistor. The resistor is nothing but load. This can be R load, RL load, or RLE load, different types of load. Also, this can also be a circuit, or it can also be a battery or a motor, etc. See, during positive off cycle, when the input voltage is positive, this diode will be more positive. See here, this is anode and this is cathode. During positive off cycle, this anode will be more positive than this cathode. So this diode will be conducting. See, normally this diode is represented here as a switch. This is used as a switch. So this will be in the closed condition when the applied voltage is greater than the cut-in voltage. So there will be a current flow. So during the positive off cycle, the current flows through the diode and it conducts. Whatever voltage is applied here will fall across the load. So we will get the waveform like this. For example, if this applied voltage is 5 volt, this output voltage will be nearer to 5 volt, but it won't be exactly 5 volt because there is a voltage drop across this diode. this value would be 0.6 to 0.7 volt as we already saw. So this output voltage will be less than the applied voltage. Okay, during negative half cycle, see during negative half cycle, so I will draw here the same circuit during the negative half cycle. See, during negative half cycle of the input waveform, here we have anode and cathode. See, this anode, see, current flows in this way, but this anode is more negative when compared to the cathode, so this will not conduct. So this current, it won't allow in the reverse direction, so during negative half cycle you won't get any output waveform. See, I will draw the positive also, but during negative half cycle you won't get any output voltage. Again the cycle repeats, so again you will be getting the positive and negative. I will draw the in negative half cycle. See, during negative half cycle of the input waveform, here we have anode and cathode. See, this anode, see, current flows in this way, but this anode is more negative when compared to the cathode, so this will not conduct. So this current, it won't allow in the reverse direction, so during negative half cycle you won't get any output waveform. See, I will draw the positive also, but during negative half cycle you won't get any output voltage. Again the cycle repeats, so again you will be getting the positive and negative will be always 0, since this diode is conducting only in one direction. So the voltage drop across the load will be always 0 in the negative half cycle. So this is the working of half wave rectifier. If you see here, the current is only in positive direction and no current flows through the negative direction. Then comes the full wave rectifier. In full wave rectifier we have full wave rectifier with center tapped transformer. See, in a center tapped transformer, this is the primary winding. The secondary winding you will be having three terminals. So this type of transformer is called as the center tapped transformer. The construction wise, this is quite complicated. This type of transformer is quite complicated for construction. But for this working, we are going to use only this type of transformer. To overcome this, we go for another type of rectifier circuit called as the bridge rectifier, that we will see in the next session. Now we will see how this full wave rectifier works with the help of center tapped transformer. See, you see the circuit here. Here we have ground. The center terminal is grounded. Also the load terminal is grounded. The meaning of this is actually connected to the load. Okay. Now we will see the working of the full wave rectifier. See, during positive half cycle, just I will draw this circuit again. See here, this is the diagram of full wave center tapped transformer, full wave rectifier with center tapped transformer. This leg is connected to a diode D1 and the other leg is connected to the diode D2, and both are connected together and it is connected to the load RL. These two center tapped winding and the load is connected together. This is the actual circuit. Now we will see how the circuit behaves during positive half cycle and negative half cycle. See, I will draw the positive half cycle in blue color. So during positive half cycle, here you will be having positive. This diode D1 is forward bias because the anode of diode D1 is more positive. So current from this transformer will flow in this direction and it flows through the positive of the load. See, this will not allow current in this direction, because here we have cathode. Current flows through the positive of the load, then it reaches the center tapped transformer, and current will be circulating in this fashion. In this fashion, current will be circulating. So during positive of the load, my output voltage will also be positive. As we already said, the amplitude will be slightly reduced when compared to the input because of the voltage drop in the circuit. This is about the positive half cycle. Then negative half cycle. See, during negative half cycle, the waveform will flow in this direction, the current will flow in this direction. So diode D2 will conduct. This is the diode D2. So current flows in this way. Also during the negative half cycle, current flows through the positive of the load. Current always flows in the positive of the load, and it reaches here. This is the direction of the current flow in the negative half cycle. So even though the input waveform is negative, current always flows through the positive of the load. So my waveform will come again in the positive direction. If you see here, when compared to the previous case, in the negative half cycle there won't be any voltage, but in full wave rectifier, in negative half cycle also you will be having some voltage. So this cycle repeats. Again you will get again you will be getting the waveform in the positive direction. Again you will be getting the waveform in the negative direction. So this will be the output voltage of the full wave rectifier with the center tapped transformer. This is the actual working. See, the major disadvantage is the center tapped transformer. Center tapped transformer. Compulsorily you must use this center tapped transformer in this circuit. So to eliminate this center tapped transformer, we are going for some modification in the circuit such that this transformer is completely eliminated. So we are going for bridge type rectifiers. Bridge type rectifier, which will give the same similar output with reduced loss. Now we will see full wave bridge rectifiers. See, this is the rectifier circuit which is commonly used for many practical applications. So this is the actual circuit diagram of bridge type rectifier. See, if you see here, the center tapped transformer is completely eliminated. See, instead of that we will be having additional 2 diodes as you see in the circuit diagram. See, we have D1, D2, D3 and D4 numbered in such a fashion that depending upon the conduction they have numbered here. See, this is the input waveform and the output waveform. See, now we will see the actual working of full wave rectifier. See, first of all I will explain the working with positive half cycle. This is the positive half cycle of the input waveform. Now if I give positive waveform to this bridge circuit, this diode D1 and D2 will be conducting. You see here, during positive half cycle, current will flow in this direction, so it cannot go this way. So this diode D1 will be forward biased, which the forward biased in the case it is greater than the cut-in voltage of this diode. So this diode D1 conducts, so again it cannot flow in this direction, so current flows through the positive of the load. So whatever voltage is applied here will be coming across this load, so current will flow in this direction. So it cannot go in this way because it will directly short circuit. So this diode D2 will be conducting and the circuit will close in this fashion. So current will flow in this direction, diode D1 will conduct, then it flows through the positive of the load, then D2 will be conducting, then the circuit closes in this way. So now during positive half cycle, these 2 diodes conduct, current flows through the positive of the load, so my voltage will also be positive. So my voltage will also be positive. Now I will explain the negative half cycle with different color. I will use green color. During negative half cycle, current will flow in this direction. Now the diode D4 will be conducting. In negative half cycle also, during negative half cycle also, the current flows through the positive of the load, then it flows through diode D3, then it reaches the source. So it starts from here, from the negative half cycle, it flows through D4, then again positive of the load, then the diode D3 conducts, then it closes the circuit. So even though it is negative half cycle, my current flows through the positive of the load, so my waveform will be in the positive direction only. Similarly, the waveform repeats, negative half cycle waveform repeats, and also the positive waveform repeats. Combining these two, we will be getting the total output, which is similar to that of the full wave rectifier with the standard tapped transformer. The only advantage is we have replaced the standard tapped transformer. See here, we will be having both positive half cycle as well as negative half cycle in the same direction. So this is a DC output because we have only positive value. Either you must have positive value or completely negative value. So we have only positive value here. It is called as DC output, but it is a pulsating DC, as we already saw. It's a pulsating DC. To change this pulsating DC into a direct perfect DC, a simple circuits are used called as filters. Filter circuits must be used to eliminate this pulsating DC and to get the perfect DC. This is about the rectifiers. Finally, we will see the overall efficiency of the rectifiers. Take half wave rectifier has an efficiency of 40.6% and full wave has an efficiency of 81.2%. Instead of half wave, full wave is more preferable since the efficiency is very high. That too, bridge type of rectifiers are used since we are eliminating the transformer. Thank you. We will see in the next session.